Okay, in this chapter we will talk about the determinants. This is chapter 4. So in the first section we will talk about the determinants of two matrices, 2 by 2 matrices. Then we will talk about the determinants of bigger matrices. So look at the definition. The definition of 2 by 2 matrix, the determinant of 2 by 2 matrix. This is the 2 by 2 matrix, general matrix. Its determinant is defined as, so the notation for the determinant is the straight lines instead of these kind of square brackets. So whenever I will write the straight lines, this means I am talking about the determinants. So the determinant of this is the multiplication of these two main diagonal entries, which is AD, minus the multiplication of these two entries. This is the definition of the determinant of a matrix. So let's do an example. In this example, we have to compute the determinant of this matrix. Here is the solution. So in order to compute the determinant, as I have told you that I will draw the straight lines to show that I am doing the determinant. So first of all, I will multiply these two elements, 3 times 4, then I will write minus, then I multiply these two numbers. Since this is 12 and this is also 12, 12 minus 12 is 0, so the determinant is 0. On the behalf of this example, I will talk about a theorem. The theorem is a matrix A is invertible if and only if the determinant is not equal to 0. So before going to the proof, let's talk about the mathematical statements. Let's learn how to prove such kind of theorems. This is the conditional statement called if P then Q. This kind of statements we use in our daily life. So in this kind of if you have to prove this statement, the first thing we have to suppose and the second thing you have to prove. Okay, in this kind of statements, the first P is assumption and the Q is to prove. Let's do an example of this kind of statements in our daily life. For example, if he works hard, then he can pass the exam. So this is if P then Q statement, and you can check that this thing is P statement and this is Q statement. So if we have to prove such kind of statements, we have to assume that he works hard, and then we have to prove that he can pass the exam. But this is called conditional statement. Okay, but we have biconditional statement. So what are biconditional statement? In order to understand the biconditional statement, let's revisit the conditional statement. The conditional statement is if P then Q. So in this kind of statements, we have to assume that this is true. We have to prove that this is also true. So what are biconditional statements? Biconditional statements are two-way statements. In these kind of statements, we have two things. The first thing is if P then Q, and the other thing is if Q then P. You can see. So in the first part, I have to assume that P is true and I have to prove that Q is also true. But in the second part, I have to assume that Q is true and I have to prove that P is also true. Such kind of statements can be represented mathematically in this way: P if and only if Q. Whenever I will write P if and only if Q, that means this is biconditional statement. What does that mean? If P, then Q, and if Q, then P. Okay, so this kind of statement has two parts. So how to prove these two parts? Let's look at the first part. In the first part, I have to assume that P is true and I will prove that Q is also true. So in the first part, I will assume that P is true and then I will prove that Q is also true. This is the first part, you can check. Okay, in the second part, what is the second part? The second part is if Q then P. What does that mean? I will assume that Q is true and I will prove that P is also true. So I will assume that Q is true and I will prove that P is also true. Now we can come towards proof. So first we will prove the first part. I will prove the second part first, because in this theorem this statement is P, this statement is Q. So the P statement is a matrix is invertible, the Q statement is the determinant is not zero. So I will prove the second part first. You can prove the first part first, whatever you can do. So I am going to prove the second part first. What is the second part? In the second part, we have to assume that Q is true and we prove that P is also true. Okay, let's do the second part first. In the second part, we will assume that Q is true. So what does that mean? What is Q? Q is determinant of A is non-zero. So I have to assume that determinant of A is non-zero. So what I have to prove now? I have to prove that P is also true. So we will prove that A is invertible. P is true means A is invertible. Okay. Since our assumption is that determinant is non-zero and we have the formula for the inverse of the matrix, that formula is 1 by the determinant of the matrix times adjoint of a matrix. Adjoint of a matrix means that we have changed the elements of the main diagonal and we have changed the signs of the elements along the other diagonal. So this is called the adjoint of a matrix and this is the determinant. Since the determinant is not equal to 0, therefore I can write 1 by the determinant, and this is the formula for the inverse of a matrix. What does that mean? This means inverse exists. When inverse exists, this means the matrix is invertible. Hence A is invertible. So we had assumed that Q is true and we have proved that the statement P is also true. So the second part is done. Now I will prove the first part. In the first part I have to assume that P is true and I will prove that Q is also true. What is our P? Our P is this statement. So I will assume that A is invertible. And what is Q? Q is determinant of A is not 0. So this statement I will prove. So what I have to assume, A is invertible. So let's assume that P is true. That means assume that A is invertible. We have to prove that the determinant is not 0. Okay, this is our aim, to prove that determinant of A is not 0. I told you previously, in mathematics, when you have to prove something, usually you have to assume on contrary that this statement is false. Okay, so I will assume on contrary that this statement is not true. So if this is not true, then what is true? Then I will assume on contrary that the determinant is 0. Okay, so I will assume that determinant of A is equal to 0. Then what will happen? If the determinant is equal to 0, then by reduction into the echelon form of matrices, we will get the last row 0. If the last row of the matrix is 0, then the matrix is not invertible. But this is contradiction to our assumption. What was our assumption? Our assumption was that the matrix A is invertible, but here we are getting that A is not invertible. This is the contradiction. So this contradiction says that our statement is true, hence the theorem is proved. Now look at an example. In this example, we have given a matrix. In this matrix, we have to check whether this matrix is invertible or not. So what we will do, we will find the determinant of this matrix. So the determinant of this matrix is the product of these two terms and then the product of these two terms. So this is 1 times 6 minus 3 times 2, which is 0. This means the matrix is not invertible because the determinant is 0.